Okay, so now we're going to talk about the tangent vector. Our ultimate goal is to understand how acceleration is related to the curvature of a curve, but for that we need to study some other things first. So the idea is that if you have a curve in space, it could be something like this. Well, there's always the three unit vectors I, j, and k, which I'm drawing here in orange. And you can imagine having like a copy of each of these attached to each point on the curve. So there's like a mini coordinate system on each point of the curve. The thing is that in a sense, that coordinate system is not it is not adapted to the curve. So, for example, it's more useful to, instead of using, let me show you this. So you should think of this as I, j, and k. This is like the coordinate system. So you can have them attached to each point of the curve, but the idea is that it's more useful to somehow rotate them, rotate them in such a way that they move along with the curve. Okay, so if the way we do this is by finding what's called the Frenet frame, which is like three unit vectors adapted to the curve. And let me just say that, write it down. So the idea is that instead of I, j, and k, you'll have one, let's say maybe this one, which would be called the tangential vector. There's another one called the normal vector, and there's another one called the binormal vector. And so what we want to do is try to define them in a way that seems natural to the problem at hand. And so for this video, we'll talk about the tangent vector. As the name might suggest, the tangent vector is supposed to be tangent to the curve. So again, if this is the curve, you want to think of the tangent vector as like maybe being here, and then here, and then here. So t will be called the tangent vector. Now, there's already a vector that you know, which is tangent to a curve. That's the velocity vector, right? Now, so there's already a candidate, which is the velocity vector. Then there are like two issues if you try to use a velocity vector. So the issues are the following. One, which is like the more mathematical problem, is that the magnitude of v may not be 1, so it may not really be a unit vector, and it's sort of convenient to work with unit vectors. So the norm of v may not be 1. There's another one which is more philosophical, if you think about it from the physics perspective, which is that v has units, right? So v is a velocity vector, so it has units of, velocity has units of like length over time, like miles per hour, meters per second, right? And so on. And it's somehow more useful to have a vector that's universal in the sense that it has it's dimensionless, so it has no units. Okay. What ends up happening is that you can sort of solve both of these two issues simultaneously by rescaling the vector, and so that's what we will do. And so the solution is to rescale the vector the velocity vector. And so our definition for the tangent vector at a point is just the velocity vector divided by its norm. Okay? And that's what we're calling the tangent vector. So notice that, again, the velocity vector, like for example, has units of feet per second or meters per second. Those are the same units as the norm of the velocity vector, so any units will cancel when you take the ratio. And so this has no units, it's dimensionless, and it also has size 1. So, and it continues to be tangent to the curve because this is just a rescaled version of v. And remember that if you just rescale the vector, you change its size, but you don't change its direction. And the direction is the only thing that we care about to say that a vector is tangent to the curve. Okay? So let's do an example about this. So as an example, let's find the tangent vector through this curve. Let's say that the curve is t squared, t cubed. That's the equation of the curve. In order to find the tangent vector is very easy. You compute the velocity and then divide by the norm of the velocity, which is known as the speed. I may have said that, or maybe I haven't, but so the velocity is just a derivative of r, so it's 1, 2t, 3t squared. Then the speed is the magnitude of the velocity, which, remember, the magnitude of a vector by Pythagoras is just like the square of the square root of the sum of the squares of each entry. So it's 1 squared plus 2t squared plus 3t squared, and that gives you 1 plus 4t squared plus 9t to the 4. Okay? And now the tangent vector is velocity divided by speed, and so the tangent vector happens to be 1, 2t, 3t squared divided by 1 plus 4t squared plus 9t to the 4. Okay? And so this is a very straightforward computation. The next video, so again, we're trying to find like a version of ij and k that moves with the curve. So this is a good vector because it already follows the curve in the sense that it's tangent to it at every point. The next video we'll find the normal vector, which is not so clear why we'll see that it's sort of reasonable why to define it, but the real reason why it would be useful is because it will appear in the formula for the acceleration. but that will wait a little bit more. So next time we'll talk about the normal vector.